Okay, good morning, everybody, and welcome to yet another exciting week of building systems. I hope the sound is okay, both online and offline. Today, tomorrow, as usual, are very busy days. So let's see if we can see today all related to windows and tomorrow all related to curtain walls. Probably not, but let's try. In the photo, it is our JCon before demolition. The first thing they took out were the windows. So some people ask it about things about the plinth. Well, there's something which always causes some kind of a doubt. Is this line here? We commented, this is the excavation, right? So people, to be able to work, have to open this space, right? The second part is the meaning of this area there. There are many questions of what to do with the waterproofing ending point, and there is not clear solution. That's always a difficult decision in terms of design. So this is one project we saw already materials, which you see, this is all curtain wall. You have the base. Of course, this is already the concrete wall going to the basement. So you see some kind of acrylic paint, and then the gravel with the drainage pipe. This is very graphic. So with the time, the gravel has been lost, right? But this is the perforations that let the water be collected somewhere. And this is just a concrete brick which separates the gravel from the sand, right? See how, well, this is porous pavement, but see how always there's a gap between floor and building, so the pavement can expand. This is next doors, right? So you see how this is just plain gravel, put wider area, and you may notice there's a small aluminum plate between the gravel and the sand. So this separates the garden sand from the gravel, so they don't mix. The facade is thin. We may see some photos of the construction in another lecture. And what we spoke, this is very sensitive material. If it is in the ground floor, it gets bumped. I don't know how this happened, but always the lower part of the building is very sensitive against damage and doesn't look good, even though the building is new. These two more examples, this is in Tokyo. This is a real trench, not gravel, with some kind of a volcanic stone to make it look nicer and people not to lose their foot. But the problem is that it splashes and it creates more dirt on that area. This is another building. This is also in Japan, in which you have this is very, very conservative approach, right? This is almost like handbook solution. One thing that is custom in many places is to have the drainage from the roof going straight to the drainage, to the trench, and that's okay. But see, there's always some kind of risk, some kind of dirt going there. And this is in Spain. So this typical humidity by capillarity. And after the years, the wall becomes weaker and weaker. Somebody asked, will the brick become weaker? Well, if it is like years and years and years, it will erode, right? In this case, the stone is quite good quality, but it's the mortar which is disappearing, right? This is clear damage by expansion of the pavement, right? And this is not capillary distress, dogs damage. So assignment, I see many submissions. Thank you so much for working hard. I had just 3 online before I came downstairs. And this is what most people did, which is very much related to what we explained in class. Draw on the structure, naming axes, giving the dimensions, naming beams, slabs, and giving some kind of pre-dimensioning and so on, right? In terms of assignment, this is what we asked for. Specific results can be more or less correct or not, but this is what I will comment later, right? The counterpoint is the other case, which is also very common. We didn't ask anything about envelope, right? It is very clear. So it is clearly somebody who did not read clearly the instructions. And something are interesting, and this is like in between, right? This is a big difference. And it's not just the scale. It is just the concept of the structural plan. What is a plan for structures, right? This is, I don't want to repeat because quite a lot of people understood, but those who did not, it is as easy as listening back to the lecture, that area, and going to the checklists and see the explanation today, right? We don't need to repeat, but it's important point. But this is also okay, but there is like a probably 40% of the assignment which is off the subject. Let's go to the facades. We already saw the basics, the plane connection to the ground, and the basic of the facade, and now we go with windows. The image is one of the most beautiful bow windows I know. It's housed by Voisey Arts and Crafts Architect in the United Kingdom. From the inside, which often we forget to see how things feel from the inside. So this is the plan for today and tomorrow. It's quite a lot. So I will start with windows. And this is a photo from Hisao Koyama, disciple of Rich Gan in Japan. And you see how this is like a pair of equal windows, how much things can go into one window design, right? Which is very modern, but also very much Japanese in essence. So we will go into the basic requirements and then into the design. In the photo is a corner window in an old palace in Spain. So this basic, the one we are all aware, it's a design matter, right? How we design the windows gives in a big part the image of the facade. But also, very importantly, the functionality. The same as the facade, the windows is like the strong point or the weakest point, if you want to say, or the most important point in terms of regulating the view, light, ventilation, and safety. Right? The photo is the building of the first example of the trench we saw before, Taniguchi's visitor center in Rinkai Seaside Park in Tokyo. And then we have the climate control, right? With windows is the first element to regulate the air, sound, heat, apart from the lights. And this is an example of kind of Arabian style window in Spain, in an area which is very hot, so you let just the air, not the sunshine, going inside. And the problem is those functions are often in conflict. If we want to be very much to the limit, we need air to have a healthy environment, but it goes in opposition to need to have a soundproofing and energy savings. And that's very hard compromise in terms of design. And the larger the windows are, the more difficult it is to solve this problem. So this is the summary of what we saw. And I brought one summary from the book. Again, I insist, the book is a very good reference. I don't think I would have done it better than they did. So that's why I use it. And we cannot go into it. You have the full text you can see clearly in the handout. It's a kind of more detail of the functions we said, right? Interestingly, the shading, which is better outside, right? Because the radiation is better caught outside. If it comes inside the building, even if you have a curtain afterwards, you got the light, but the heat is already inside the building, right? And many other things we already know, but we will see in detail later. This is a nice summary again. So about natural light and ventilation and cleaning is the basics. So natural light, we commented, we have a simulation software. You can do very precise simulation, but there's kind of rules of the thumb. And curiously, the traditional Southern Europe is very much the latitude of Korea, right? Maybe a bit north, but it will work the same. So just like custom, the size of the room is about 1/6 of the room area, right? And usually it's between 1/5, 1/10. So in a 10 square meter room, which is a very typical bedroom in an average house, it's kind of a 1.3 by 1.3, right? 1.7. And 1.3 or 1.2 is very typical standard window, right? So there must be a reason in the custom. Then for ventilation, the custom is at least half that being possible to open, right? And that has worked for centuries, generations, and still is kind of a habit embodied, right? And with speed of natural light, it's also daylight Careful with the sunlight, because it seems we're speaking of the sunshine going straight, direct sunshine. It's not the same, right? Natural light, daylight, maybe diffuse light, reflected light, right? So we have not almost no sunshine coming in, but there is reflected light, indirect light, right? We don't call that sunlight, we call it daylight or diffuse daylight. About ventilation, there is again kind of traditional dimensioning, which comes very much, welcome, come in. You are new in class. No, this is building systems. Well, you're welcome if you enjoy it. I think it's more interesting than circuits, but maybe another classroom. Unlucky of him. So this study is mostly early 20th century with this kind of minimum housing and finding the minimum livable, healthier spaces. And the most demanding is the sleeping rooms. Because when we sleep, we consume a lot of oxygen, right? And the calculation, one person in 7 square meters, about 18 cubic meters, is like a one-time renewal in 1 hour, right? And this is why individual room 7 square meters is quite universal size, not only because fitting the furniture, but because of the air you have to breathe. That's with the traditional windows, in which you have infiltration and all that, right? Stay areas are a little bit less demanding, and it's about a bit more than half, right? So one person would be about 4 square meters for a living room. So family of 4 is 16 square meters, which curiously is very much common standard for dimensioning stay areas, right? With a 2.5 ceiling height. But the question is how we achieve that ventilation. Of course, traditionally we open the windows at the street, right? Especially with good weather. So if we cannot open the windows, traditional construction works on the filtration. Window and the sashes are not perfect. The doors are not perfect. There's always some slit around the doors. So you have just the pressure of the air coming through the slits of the windows, crossing through the doors to the other side, and exiting where's the suction of the wind. And with the traditional construction, that's usually enough to have basic ventilation, right? You can force it with stacking through a shaft, right? Which will force a little bit, will have more pressure to absorb the air even if there's no wind, right? And this is the diagram. So the joints are not perfect and the air comes everywhere. If you have slept in an old hammock in winter, you know very well the filtration, right? Especially if you're near the windows. But that is terrible for energy. It is very healthy, but all the air we lose is energy we lose. We are heating, or if you are cooling, it's also, we are cooling the environment. So there is the most basic is the aeration devices. Here's the word, it's a very unusual word in English. So something to let air in. There's like slits which are integrated in the sash or the frame in different ways, which by hand or automatically, most options are automatic, let the air come in just the right amount of air without losing much energy, right? Those are mostly Northern Europe and Canada inventions, of course, very cold countries. But now with the zero energy, it's becoming a standard even in warm countries like Spain. So we import from the north those elements. And the most perfect, the favorite of all sustainability and systems guys is the mechanical ventilation, what Le Corbusier called the exact air, right? He was very Cartesian. So you put all the air you need, no more, and you control by computer, by programming. And you may have even a heat exchanger element in which you don't lose almost anything of the energy. So you have 100% clean air and 90 somewhat % of the energy in, right? 3 great systems. They all have their advantages and their problems. This is the most perfect, but of course, it is more expensive. You rely on energy to use it anyhow. Of course, you're saving energy, but still, if there is electricity cut or some kind of malfunction, you have to open the windows, whatever. So it's not perfect. And the fans are noisy. If you make this installation, you have to think where to put the fans and have expensive ones, right? And big shafts, so there's less noise and less speed. And that's all money, right? Many of those systems are stopped because the pain of maintaining and the pain of hearing the sound, especially when you sleep at night or when you're doing something which needs silence. So that's it. It's like a 3 options we have. And there's not perfect option. Even the old style infiltration can be an option depending on the context you are working. So I invite you to make the first activity. If you don't have the sheet, you can collect it. We have 3 minutes. So don't worry, you cannot finish. The question is thinking about the advantages and the problems of each. Okay. So 1 is infiltration, 2 is aeration, and 3 mechanical. And it is like a rating from a best good to the worst bad in terms of 4 parameters, which might decide you which one is more appropriate for each case. As usual, you can discuss, you can talk, you can do whatever you want. The activity time is a time to be noisy and to move, so we don't get too sleepy. Oh. You don't mind if today I just remain here. I like to walk around just to nag you, but better not moving too much today. Okay, half time passed, 1.5 minutes left. Wow, some people already finished. Okay, of course, there's no perfect solution. There may be opinions, but I think there's a range of options in which most of us might agree. Okay, maybe 3 minutes was too much. I was thinking like a 1 minute per system, but probably not much discussion, maybe a lot of agreement. So we might continue with the next slide because we have a lot of things to do today, as usual. Well, something we comment, in most countries, we clean the windows, right? I see it is not the case in Korea, but cleaning the windows has a lot of effect in visibility and light coming in and so on. So this is taken from the Spanish, this is Spanish, but recommendation for cleaning windows safely if you don't have outside exterior accessibility, right? So in Spain, climbing from the facade would be a forbidden way of cleaning windows. It's dangerous. That's just a reference. So that in most usual buildings, housing and so on, we have a limitation on how big we can make the windows, right? Unless we have a system for cleaning them on the outside, especially. So let's go into the design, which is the funny part. And the parts, this is a very basic reminder. So most important is the lintel or head, right? The sill and the spandrel. Reveal, I see very seldom. Sometimes it's called jamb, right? But seal, spandrel, lintel, you will hear all the time. Even in Korea, you will see these words in Hangul. Then the parts, the glass is usually the sheet, right? Whatever, because sometimes it's not glass. Careful with frame and sash. Usually we mix both concepts, but the frame is the fixed part, right? And the sash is the part that moves, right? The hardware is all the handles, hinges, everything which makes the window work. And then we have, of course, the joints of the frame with the building and the sash with the frame. It's two sets of joints only, but already a lot. And then finally, the shading. In this case, it is inside. This is Mies van der Rohe in Michigan, right? So Mies van der Rohe never puts anything outside the glass. And Michigan is very cold in winter, but it is hot in summer. This is my photo. I just visited, I didn't live there, but I lived some time in Michigan, so I know what's the climate there. Then typologies, again, this is a reminder, it's mostly linguistic, but interestingly, well, we can have the windows inside. Actually, this is like in the middle of the wall, right? If we are inside, it's like a really inside, right? So this is like a halfway. And then on the exterior, which is something we see often, but it's the most difficult. Difficult to do and difficult to read. Well, the question is the protection to the outside is very weak. We have very weak points. We have to detail with much care. And this is the typology. I will not repeat because it's just knowing each. Two things to comment, right? Fixed window, of course, is the one with less infiltration. That's obvious and the cheapest. And the sliding windows, jalousie or accordion doors have a lot of infiltration, so they're not very good when you need energy. And the rest are something somewhere in between, right? For the sliding windows, we just put an arrow in the direction it slides, horizontal or vertical. This is a special case of a sliding window in which it has to be like put inside the floor. It reaches a little bit and then moves. So you have a sliding window, but with good imperviousness against air, without much infiltration. And the most common are the hinged windows. This is how we draw the hinges in the States and in Korea. I don't remember about Japan. So if the window opens in this direction, that means this is a hinge. The dotted line will point at the hinge, right? So US, Korea, I'm not sure about which other countries. In Europe, I'm sure, because I worked there a long time, it's just the opposite, right? If this is the hinge, the line just goes in the opposite direction. So be very careful, because depending on the context, it might mean different things. And the way of opening the windows is not always obvious, right? So it may depend in the inside. And those central hinges, especially vertical, horizontal, those are great, very well balanced, but very hard to detail and to build. So they are among most expensive. So this is just the same, but a bit more by families and with photos of each. The ones which have tilt and swivel can open with two hinges, right? This could open also in the other way. This is just a question of the hardware, right? It's a bit more expensive and it's a bit tricky to use, but this is something which helps to have ventilation without having too much energy loss and without taking up much space. The problem with windows opening to the inside in general is that you need a lot of space to open them. And this is the others we said. And then, well, bay window or bow window. And the clearest story comes from the old churches, this tall windows, right? Which you will see of an architecture. This is Frank Lloyd Wright's. And for some reason, French window is a window and door at the same time. I don't know why, but how it is called in English. Okay, let's go into the materials and modules, which is more important for us because it's, well, apart from the typology, right? So this is kind of summary of the most common materials. This is the parts we saw before, right? So we have timber, steel, aluminum, PVC, and other. There is like almost any new material which is hard enough has been tested to use as a frame, right? But this is the most common. The sheet most common is glass, but we know paper, traditional architecture, and very often polymers. And sometimes it's like a solid window with just timber or plastic or aluminum, not really window, right? Joints, most common are neoprene. In Korea, everything is silicone, which is great for LG Chemical or Hanwha, those guys, but not for the windows. All before silicone, it was bitumen, some kind of asphalt. And of course, we can use just the design to use trims, overlaps. So we don't need always to have this kind of sealing material, right? And hardware, most common is steel, stainless steel, sometimes aluminum, sometimes polymers. And in high quality windows, you may see brass, bronze. Mies van der Rohe in Michigan used I think it was brass, right? And then shading can be almost anything, right? Regarding the sashes, there's kind of a most common sashes from timber to concrete, which sometimes we can see, with strengths in insulation, in mechanical strength, maintenance, and the possibility to customize. There can be opinions, but more or less this is kind of correct. So depending on the kind of project you have, if you want to do something custom, it will be easier you work with timber or with concrete, if you can do it, than with aluminum, at which case you need to have like a big commitment of the client to work with a extrusion company and design and fabricate a custom profile, right? And this is notes. Okay, so we don't need to speak a lot. And this is some of those old buildings which disappear little by little, but I think they have the charm of this kind of steel frames and sachets, which are very thin because steel is strong enough to hold the glass. So it's very elegant in their own way, right? And very light windows with plenty of proportion of glass. The problem with the steel is that mechanical strength is great, thermal performance is zero. But we have makers creating steel frames with a thermal break. I didn't bring them here, but you can find them. They're very expensive now, but it's interesting to have a possibility. And we have, this is another example to overcome that. This is a Japanese maker, Sankyo, very expensive, which has all the set from just a fixed window to a full curtain wall with the same front, just 6 centimeters, right? No matter how much you need. And if you need strength, it is just by adding timber to the back. So it's a very good combination, very intelligent. You know, when you make a window, of course, at small scale, we draw the partition, whatever we design. But if one element is fixed and the other is hinged, in reality, the hinged part will be thicker. And that makes windows a little bit asymmetrical, and you have to really work hard with the design, right? Especially if the windows are small, but in all cases, they don't look good. And this is one way to avoid it. You can find in internet, I give you the data, and this is one example of thick curtain wall with an element which can be opened, and whatever you do, the system allows you to fit everything in 6 centimeters. So this place for creativity. Then sizes, our black beast. We have to work on a scale and be aware of the real size of things, right? And the limit, as always, is mechanical strength, the fabrication limits, and then the handling. How will you assemble things, right? So mechanical strength, usually the makers have a table, and you have to check, especially you work in very extreme environment, right? And in Korea, we have typhoons and big storms. So in some areas, you may want to make sure the glass and the sash stands those actions, especially if the windows are very big. Then the fabrication limits, right? And this is the materials course. So we cannot understand everything without knowing that course. But usually, very few makers make glasses larger than 6x3, and very few ones. And if it is safety glass, even less, 2x4, more or less. Can be 4.4 or something, but most makers have difficulty to make things bigger than that, right? And there's the sashes. You may do something in custom and have the engineer and the mockups and the laboratory testing them, but if you go to commercial sachets, usually sliding like 2 by 2 more or less, a bit more, and hinge it like a bit less, 2 by 1.4, 1.5. And this is based on the calculation of the hinges and the strength of the frame at the sash, right? For larger elements, you have really to go to custom solution and be very clear with the maker and the construction company. Otherwise, you may have a disaster. So it's an example of one building which is just finished here in Myeongdong, DMP, one of my friends. And he was commenting on the glass. This is like the largest glass, safety insulating glass you can buy in Korea, right? The building next door, which is the same office, has the Apple store almost opening. They have the huge glass, which comes from an Apple-owned company in China. Right? You have to pay for that. Just as an additional comment, the steel of the panels is black stainless steel, very expensive for 2 millimeters. The architect was a bit upset because if you look nearby, it is welded on the back, but you can see the bumps of the steel, right? 3 millimeters would be ideal, but it's 50% more material, and it was very painful for the promotion. But well, nice, elegant curtain wall. This is a renovation, by the way. The upper part of the building is as it was before. Then we have the handle and transportation. And the first thing we have is the weight. Glass is as heavy as a stone. It has a huge density. So the 3 by 6 with a reasonable thickness would be more than half a ton already. Handling that is a nightmare. In that size, you might break it as you handle it because you may create unwanted mechanical actions, right? Right. And if you have fabrication defects because the cooling is not perfect, you may crack it spontaneously. It is quite tricky. The use also is a problem. If we have a sliding door of the maximum size, that's 150 kilograms. To slide it is almost on the limit of what most hardware we can have. Will demand very expensive custom solution, right? And replacement, if the glass is very big, you cannot bring it to the elevator. You need a crane from the outside. And that's very expensive, right? If you are even in the second floor, if one window here breaks, well, this is probably may go to the big elevator, but in most cases, it couldn't be, right? So something we have to think ahead. This is how we transport those large glasses. And this is not 6 by 3, right? It's maybe the 4 by 2 or 4 somewhat by 2. And this is the construction of the Willis Fabre building we will see tomorrow by Foster. This is one sheet of glass, and you see the guys working there by twos and quite strong guys, right? We have to know more about glass, but I left you the link to the lecture of 2020, 2 years ago, and the PDF if you want to refresh your memory and enjoy all of the great YouTube videos we have in class. We have to continue the joints, and as we said, joints are our life in construction. And this is familiar because we saw already in materials, so I will go a little bit fast here. This is a case of the window in, right? So this outside. The first thing we do is, as much as possible, design the wall, the lintel in a way that the wall protects the window as much as possible, right? Both horizontal and vertical. The same in this section, this horizontal section. So you see this, the wall covering most of the frame, right? Right. And you have even one more element and 2 elements, this is overlapping. So to close these joints as much as possible, right? Overlap, covering the joint with another element. And then this is quite sophisticated window, right? It is just one shape to hold the glass on one side and one cap to fix it. So this glass can be replaced from the inside with elastic joints for the glass to be fixed. No silicone, if you can. And then one small element to give some kind of cap between the glass and the sash so they can move, they can deform, they can expand independently. Many times glass cracks or breaks because of not respecting this kind of small gap, right? Just a few millimeters. And then inside we have the same kind of overlapping to lock the joints, right? And the window has like 3 points of contact. So that means that it closes 3 times, makes more difficult the water and the air to come in. And to make it even better, you have, let's put in neoprene joint, which just closes by pressure, right? And if we're unlucky, the water comes in, it will slide down, right? It will slide down and will be just rejected through an exit pipe. We can simplify this as the frame as a kind of element, right? And the sash like kind of element which collects the glass plus 1 cap. This is a simplification of this. And this is the most common window, just 2 points of contact. And with this principle, you can understand almost any frame and sash. 1L plus 1Z, right? And that works in most cases. And to make things work, we try to use the same section in all sides of the windows, right? If we go to the top, this is the easiest because the water will have very little impact here, only the wind will have, but the detail is exactly the same. But this done in a way that if we are unlucky and the water enters this way, by gravity, we'll get out again, right? And then you go to the black beast, which is the one we did in assignments and we did in class, and we redraw and so on. And this is exactly the same frame, but it needs a special solution because this is the most dangerous part. All the water accumulates there, right? So we have the basic Z element, right? The L in this case is totally solid, right? Because instead of having that kind of L, actually, if we have the aluminum part, it should be an L shaped, right? With a small protrusion. What they do is to create drippers, right? And in this case, it has 1, 2, 3 drippers. So the water does not slide inside. So the dripper. Then they have some kind of 2 chambers. They just reduce pressure. If the wind goes to the slit, as it expands, the wind just slows down, right? And it slows down again if you are very unlucky. So sometimes those chambers are called decompression chamber, but well, just air chamber. The first one, which is more exposed, has a weeping hole, right? So if the water accumulates, can go out again. And then we have the 4th element, which is the neoprene or the joint, right? So this is a very sophisticated, very modern window, right? In most cases, you don't have this happening twice, maybe only 1 chamber there. That's quite intelligent. And in this case, if the water accumulates, it's not wrong here, but in many cases, you have kind of conduction, right? Kind of drainage pipe or sensor line. So the water accumulates can go out by gravity to the seal. So we have like 5 elements. And then 6, of course, we have 1 element overlapping the joint of the frame with the seal element. And the seal is much longer, right? We are seeing only a small part of the window. One thing I corrected here, let's clean a little bit. The book just puts the screw going to the seal. I don't see it because the seal is a cold side, it is delicate, it's very aggressive. Well, it has a lot of aggressions, not very fixed. So I think it's better to fix it to the solid part of the building, which is the most usual. You will fix to the lintel, to the walls, and to the under part. We will see later in the details that it's not so easy, but fixing to the seal as the book draws would be my last option. Okay. But well, it is in the book, so if you do it, you have a reason for that. But there are things I really don't see why they do like that. I put some outline to make clear the caps and the elements because the drawing was not very clear there. See how the neoprene element usually is not totally embodied in the timber. So the timber has not this shape usually, but the timber is flat. Those elements just allow to have the pressure to make a good contact, right? rather than having the continuous neoprene there. And if we understand that, going to more complex windows like PVC is very easy to understand because we have the Z element, right, with the L element. This one intermediate element to fix to the fabric or to the wall, and then the cap, right? So the basics are exactly the same. PVC needs reinforcement because it's very soft, so it needs some kind of steel angle inside. And the more layers it has, the more air chambers, the better it adds as insulating material. And I would add a tripper, which is not very trendy. It doesn't look good outside, but will be better. See how it has already the shape to collect the water, and eventually it will have some kind of hole to evacuate. This is, again, a very difficult to see, quite a common window from a famous book, right? Mesa. It's one of the handbooks we use sometimes, and you have in the library. What is interesting here is what we commented, I think, yesterday, the window being just in line with the insulation area, right? In this case, a bit more outside, not with the solid part of the wall. So in this case, what they do is to have an intermediate element, in this case timber, to fix to the solid part of the wall or fix to the solid part, and then the window fixes to this intermediate element, right? Same in the lower part. It's not fixed to the seal, it's fixed to this element, which will be fixed to whatever structural element has the wall inside, right? But if you go to the window, this is aluminum and it has insulating elements in between. That's the thermal break. Right, it improves much more the insulation. But again, if you see the detail, the window is like the Z element with the cap, and then the base, which in this case is a bit more simple with some very, very subtle element on the top, right? And this is more examples, a bit more sophisticated, more modern, but without myself explaining much, you are able to understand how they are done. And you can fabricate, you can design your own windows if you want. This is very common, the outside to have some kind of aluminum to help to improve the function, right? To give more protection. And this is more cases. I brought this because you can see basic thermal break, a bit heavier thermal break in case of aluminum, right? The exterior side. So this black is a polymer, which is very insulating. So it gives the continuity of the insulating glass with the thermal break. Okay, and that's okay. What we said, the thermal break is a very specific polymer, and not all makers give a clear specification. Maybe we have some kind of industrial secret in some commercial products, right? So polyamide is a full family of polymers, but it's the most commonly used if you want to see how it happens. This is quite interesting. This is taken from the Detail magazine, but it's already more than 5 years old. But it tells the evolution of the sachets from 1950 to just 8 years ago, right? How simple were things when Le Corbusier and Alvar Aalto and those guys were doing windows, and how complex they became just to achieve the thermal performance we need. And you see that in the glass, we have not much choice, just adding layers. And triple glass is almost on the limit of what you can fabricate. And the other element is just to work on the sachets. See how sachets become thicker and bigger. That means making elegant, slim windows becomes more and more difficult. This is a more detailed case of the study for the timber windows, right? And they have 2 sets depending on the power of the glass, U1.2 or U0.6. This is extremely difficult, right, to achieve, right? This is already a very good glass. But you see that in the most exaggerated case, you go over 1. Many codes are demanding a global U of 1 for the whole window, right? And this is just a relatively small window. This is a window 1.2 by 1.5. Just not a big window, right? If the window is bigger, you have more troubles to do it. And of course, The perfect one is to have 5 layers of glass and 2 closure with 1, 2, 3, 4, 5 closure points. That's great, but see the cost, the difficulty, and the little air you get inside. In this case, you need urgently some means to put oxygen, to put air inside. In aluminum, it's even more complicated, right? They didn't draw the double window, the closest we have to the double window, but you see the thickness of the sash or the addition of insulation layers and always triple or quadruple glass, right? So, and in this case, we are in the limit, right? Complying with the codes for energy is a real challenge. So I think the traditional vision of the sashes, when things become so complicated, maybe either we change the codes or we change the way we understand Windows, right? So this is some makers table for the glasses. I go is insulating glass unit, double glass unit, triple glass unit, right? And you see that with the chamber of air, with double glass, it is impossible to get to the 1 we said before. Only with triple glass, we have 0.7. But we need to have argon. That increases the cost a lot, but only with triple glass, we can go below 1, right? And this already with a chamber of 60 millimeters, which creates really, really thick. Window needs a very thick sash. Right? This is the performance, right? Depending on the total width of the window. So the technology is very much in the limit of what we can do. And you know, if you see this light transmission, we go from 70% of light to 50%, 55%. So half the light is blocked by the glass. Right? And half the light is a lot. Actually, 70% is a lot already. And triple glass makes the window 50% more heavy, as we know. So it's all difficulties. So one thing we commented in materials is the very thin glass. We have already technology to make glasses of 1, 2 millimeters, which may be much lighter, right? I think we lost the connection in the main computer, but now this is taken over. So the transmission is cut in there. What I don't know is about the recording. I hate the recording being cut. Well, since we are in Zoom, while I try to do it, this is the detail we saw. I just completed the seal. Just on your sheet, try to remember, we said like 6 features of the window. Remember at least 3, point them, name them, and write in your sheet. But let me see if I can fix this so we can continue the recording. Otherwise, we will record on the cloud. Okay, I think it was not. Okay, I think it has to. Okay, let me see if I can fix it. I'm sure you did perfect. Okay, so let's continue. How are we at what time? Okay, so let's see if we can continue. So some of you asked about the importance of the dripping device, and this is very important. So the joint of the window with the wall is extremely weak and extremely delicate. This is why in the examples we saw, the wall is just wrapping around. We have even more elements which cover that kind of joint to make the water difficult. But it's an example of one window. This building may be about 40, 50 years old. And this is a window which is on the outside, right? And this humidity here, just infiltration through the joint. No matter how much silicone they put here, if you have a wall with a frame, even if you fill the joint with silicone, this element is porous, right? So the water will infiltrate to the inside, whatever you do. There's difficulty. And you see what happens, right? So it becomes a real disaster. But curiously, you will expect only the water be in the most weak way part against water, but even in the top, you have the water sliding from the full facade and finding a slit where to go. So see the same building, the same orientation, a window which has a small dripper, right? In this case, this is totally clean, right? And this is just this device. Of course, the distance to the wall, having the windows inside, makes things easier, but surely in the lower part, as you get more exposed to the water, the problem will become a bit worse. Let's try again. Okay, let's see how long it works. So shading, not much to say. We have, this is from the book, and you see that all the examples show the shading on the outside, right? Which is the proper place of putting the shade, where it's more effective. The one with rollers outside is the most common. It's very easy because it has almost no space, and you can change it to have the rollers having some gap to get some kind of air. And the one with flat elements, which you can collect on the top, are the most common. You can find in the market elements which go the opposite, which go from the bottom up. So you may have light coming from the top, which is quite interesting, and you block the view. All of them made in Swiss at a Swiss price, okay? And then I think shading is important not only to block the sunlight, as it happens with those shutters, in diffusing the light. If you have a direct sunlight, right, in one room, you would have a lot of glare. You have an area very, very brilliant, another area with a lot of shade. With a huge contrast, you will be in difficulty to see. Slight diffusion will make very, very regular light to very deep areas, right? So you have very, very, and this very simple, very cheap, and very effective way to treat light. And you can regulate depending on the amount of light you want. So it works very well. This is one example of those rolling shutters, right? This is in Madrid. And this is how the detail works. So it's just one box. You have the roller and it slides, right? As you see here, it slides on the outside. The weak point is that you are interrupting the insulation, in this case, the screen. So you have, again, a weak point for noise and heat, but it works very well and doesn't take a space. This is the one of the flat elements, which in this case, they collect to the top, right? Well, this is here in Korea, like more made to order wooden shields. This just fixed shades with punched metal, Toyo Ito. And this is in Madrid for with just a straw, right, a bamboo. It was published everywhere. The owners hated it because they thought they were kind of hot, not in a real apartment. And then we have the green shading. This is here in Tondemon. This was the Seoul Hospital. Now it's kind of Tondemon, the museum of the wall of the city of Seoul, whatever. Just designed to have plants. So the plants dried the first year, right? So you make a green wall to make sure the plants can be maintained. Otherwise, you have a small, strange result there. Right? It was supposed to be totally green on the outside. Never happened. But green is a great way to have shade. You have deciduous plants. You have plenty of shade in summer and plenty of sunshine in winter automatically. Only you will need to make a lot of cleaning in autumn. Light shelves is more common. I am sure you saw it somewhere else. That's interesting. So what we said about the diffusion can be very much improved by the use of light shelves. You need very tall windows, but in deep spaces, right, you will have a good light near the window, as it happens here. About half the glass has nice light, but the rest doesn't get so much light. So the light shelves will just reflect it, and you'll have light in a very deep area without much effort. There are many variations. I show you a few examples. What are the problems? First, you need very large windows, right? Otherwise, it doesn't work. And second, they need cleaning. So those elements are perfect accumulators of dust and dirt. And if you don't clean like once a week or so, they lose the efficiency, right? So it's the basic example. If you can regulate the angle, you may just fine tune regarding the needs of the light. So see how you have the diffuse light with the louvers and then a strong reflection to the later part of the room, right? This is a bit lighter, so this kind of diffusion and light shelf inside, this is like a very soft, very light use of it. But still, you need to have a nice maintenance of this part. Those will not reflect light. And more sophisticated, in which you can calculate the angle to have the perfect light all around the year, right? Again, this needs a glass. In these areas, you have to clean both the glass and the mirror. Again, it's quite interesting, and you see examples, but they're not widely used because of that practical problem. So interesting case, again, we will have, again, the stereo glass, but you can change the angle of the reflector depending on the time of the year to have the proper amount of light. Okay, so this is the basics. Now, examples. Let's see how many examples we can see in 15 minutes. Some taken from the book. This is the example of a wall of 2 layers of masonry, brick and maybe concrete, right? See how by system the book provides some kind of protection of the wall to the frame and the sash, right? And in almost all examples, the insulation is in the line of the window, which creates the problem of how to fix it, because the window is just in a gap between 2 layers of wall. If we see the detail a bit bigger, we see very clearly, well, the seal, which is made with a brick, right? This little bit makes us a kind of cutter. Maybe a bit more angle would be more effective, right? Not cutter, of a dripper. The solution, there's plenty of solutions for this kind of lintel. You need some kind of structural element. It's kind of prefabricated concrete, reinforced concrete element. Most commonly, you will see some kind of steel angle, right? Something like that, right? And you need it for both sheets. But how do we fix this frame, right? Of course, the book suggested to go to this brick. I wouldn't do it, it's risky. Most commonly, you will have an angle fixed to the solid part of the wall and then to the frame, right? Same here, to a solid part and then to the frame. And that's safe enough. Not easy because you have to work in an awkward position. This was an example of what could be this kind of result, right? The typical window we know with a very thick wall, but probably this window is done in a similar way, maybe without that detail to the insulation area, because 1980s was not a big issue. This is a rendered wall, but the detail is almost the same, right? So I don't think we need to go further. The only difference is this is rendered, and then we have one prefabricated seal piece. Again, I miss some dripper in this point. Otherwise, the water will slide and you'll have some difficult joint there. And this is a very common case, right? This is not rendered, this is in the wrong place. This is the example we saw with the continuous insulation and those bars getting the slabs. And in this case, since it is reinforced concrete, you can fine tune the thickness to leave a gap for this kind of shading vertical movement, right? See how in this case, you need to find where to fix the frame, right? Because you have not really any solid part to do it. So probably in this case, they will have some kind of device going to the concrete, some kind of device. You see some kind of line there, right? Going to the slab. So you'll need to have an additional in-between structure to support this frame. And they don't explain how they do it. So I would find some element which goes to the solid concrete on one side and to the slab or to the solid facade on the other. But being aware that sticking to the facade will be a cold side of the wall. It is always a bit more problematic, right? And then the outside. Well, this is Toyo Ito again. This aluminum reinforced concrete. When you go to the outside, and this is very common here, you will see many places in Seoul. So see the importance in this case to have, apart from the ventilation, additional waterproofing, right? Just in case, and a clear dripper, so the water will just 2-3 centimeters enough to improve the safety by a big margin, right? And same inside, you have the dripper, and you let the ventilation there move through, right, and go in. And in this case, it is clear they are using an intermediate element to fix to the wall, which could be masonry or concrete. So we can see clearly one angle, right, which is an intermediate wooden element. So the thing we have always more difficult when you detail is how to make those joints, how to fix things really. And this will be like the biggest fight with the construction company. Actually, to make this detail here in Korea will be a big fight with the construction company. Actually, they have a much easier, cheaper, faster way to do it. And this is an example. This is, again, I think it's a Haiti Valley, Art Valley. This is all curtain facade, it's very safe against the water. So the water will not infiltrate, but see how you have this small detail there. So no matter how much flat you want to be, this small detail changes a lot how things perform. And let's see, so this is standard today. And probably with the commercial sashes and windows, you can design almost any window, thinking in those systems openings, those modulations, those maximum sizes you have to respect and the design of your building. But what I find interesting is how people did before we had commercial sashes, how they designed them. So I brought a few examples. But this is Asplund, I think. No, this is not myself. So this is Asplund, Gothenburg, or Göteborg City Hall extension. 1939, finished. Well, this is the lobby to the courtyard of the building. In 1939, to make a glass of this size was quite exceptional, right? Of course, this is single layer, maybe 8-10 millimeters thick. It's in the limit of fabrication, but see how thin is it? How did he achieve this kind of thickness? This is in Sweden, which is quite cold place. But again, 1939, they were not so much concerned about it because that lobby is kind of half public spaces, treated as half interior, half exterior space. But the detail is quite interesting and very clever. So this is the axonometric, right? The wall, there's the detail of it. It is basically two steel plates which make the strength, and the solution is same in all areas of the frame, with one good quality, strong timber cap on the outside, which is screwed to this metal, And then a different timber, good for the interior to make the finishing. So this gives a reasonable insulation to the very cold metal. You have very good combination of strength and reasonable performance for 1939. Right? It's elegant, and the elegance is in the simplicity of it. See the connection with the wall, which is also beautiful. So what we were wondering about, we have the steel plate, right, fixed with an angle or a rebar to the masonry fabric. So it's perfectly fixed. And see how we have still the same timber elements as outside. And then the render of the wall just covering those joints, so there's more protection. This is again the overlapping, which is a key word in any kind of construction element, right? Again, this is Asplund and Lawrence. This is 1 year later. Actually, he was working in both projects at the same time. And there's an interesting clerestory window detail over there. This photo is taken maybe 3-4 years ago. So this building was about 80 years old at the time. This is a local sandstone. This is kind of deteriorated, but not bad for the age. So 80 years is quite a nice age for the building. So this is a detail, and I will show just the top part first. In this case, everything is timber, but the trick here was to make a double glass before igus were invented, right? So how you do it? So you start having one piece of timber, which is fixed to the fabric, right? And just this small set shape, so it allows for that stone to overlap the joint. Never joints are exposed. And then you have an extra layer of exterior timber. So it's the good quality timber for the exterior. This is the basic stone timber for structure, right? Then here is where you put the first layer of glass, right? Then you have another bit of timber, which is nailed to the other, so the glass is fixed. In the intermediate elements, it's just another piece of timber, right, which places the glass. This is placed from the outside. And then you put the second layer of glass and another piece of nice timber for interior. This is a question of design to put another element which is always covering the joints between elements. And this hides it from the view, right? So if something happens there, maybe you get some kind of humidity or some kind of crack, you will not see it, which is also kind of trick to avoid it. And a very simple element on the back, right? Switch, again, makes a perfect window with a light diffusion for a very quiet space with double glass. And then the lower part, which again, it is very simple, but works great in its ingenuity, right? But always the lower part, this element is going around all the 4 sides of the window, but this needs a special solution. So now that Uri Minjes is sleeping, let's wake up and make one more activity. Last activity today, only 1 minute. Just, you don't need more. Tell me what's the function of K and J. And if you see it, you will understand how clever is this design in its simplicity. J and K. You can see a small dotted line after J, something happening, and the K is very clear. This is two things we commented in the window detail before. So if you don't see it well, there's very mysterious dotted line here, ending in J. What is this, right? K, I think, is very clear. You have it. This is a very great exam question, just for everybody to pass with a good grade. You have it. We have only 5 minutes left. Well, this is not original drawing. This is from the publication I got it. I would have done it slightly different, but I'm not sure how exact is this. But again, it's a beautiful detail, right? Totally made to order. And this detail could be used probably with this thickness of timber, maybe in today's standards, just changing the quality of the glass. Okay, let's continue. Alvar Aalto, since we are in the last 5 minutes, I will not comment in detail, but you will have this in the handout so you can look by yourselves and think that this could be exam question. Alvar Aalto in Viipuri, which is really cold part of Finland. It was sometime the Soviet Union or Russia. He's working very much like Asplund with steel elements, standard angles and plates. Again, the frame is conceptually 1L, right? And then the glass and a beautiful two set of timber, right, to make the interior. So you have the glass, strong exterior finish, the drip element, and the elegant wooden interior. And then again, very intelligent connection to the wall, which those elements are inserted in some way to the fabric, to the brick or whatever is used there. Villa Marea, again, 1939. Many buildings. This is interesting because it has huge windows which are fixed, but you see behind small opening with some shade. This is a solid window of timber which is used only for ventilation. So it's kind of in between traditional window and aeration device, those devices we commented before, which come from the north. So this is the full facade detail. It's interesting to see the context, but see again how in this case Aalto is working. So this is a solid window, all timber, just for ventilation. And this is the window which is fixed, which is a good solution. You can open, actually this looks like a sliding in some way. So you can operate it, you can clean, but you can ventilate without opening the whole set of windows, right? But he does work with small commercial cheap timber, and this he covers outside with more quality timbers to give the final shape of the window, right? And you have all the, again, the difficulty is in the connection with the, well, the seal part. Sianatsalo City Hall, we are getting closer to today. Again, it's not the same as one before, but very clever way to have double layer glass. So already you see it's just 13 years difference, but the standards are quite improving in this case, right? Actually, 1950s is probably the best era of Alvar Aalto. It's not that he didn't do great things after, but most exciting buildings probably is in this period between 30 and 50s. And this is the connection to the wall. I will not comment everything, but see the clever overlapping and the use of those cuts to hide imperfections, that difficult connection, right? Which is much better, much clever than putting silicon everywhere. This intermediate element. And the last one, I think, not last one, but Chandigarh, we are 1963. It's interesting because this is a custom-made concrete frame, right? With a solid metal sash or element which is just for ventilation. So it's the extreme of what we saw in Villa Marea. Here in Chandigarh, they need air, not much light because they have plenty. In very hot countries, shade is much more appreciated than very brilliant spaces, right? Because in the shade, darkness means freshness. And this is a case, again, example on how you can do it with concrete. Glass connection with the concrete is very delicate. They don't show much details here. And in this case, they have some kind of asphalt. Probably nowadays would be this case, the silicon, right? Maybe in this case, we have not much choice. Salk Institute to scan, again, this area is, again, all timber solution. This is California, so thermal performance was not a worry as it happens in Sweden or in Finland, but yet the basic commercial low-grade but strong timber in the core, and then the finishing outside with a more quality timber for the exterior and integrating the frames, right, is quite interesting in the solution of the sill in a structure which is called timber, which is an example we don't have in the book. And this lower part, the solid part, the spandrel solution. And I brought this. This is like a worst in terms of performance, but very elegant solution of one window made with just two elements, right? One steel cross and two angles, right? That creates a very elegant window, terrible in thermal performance, but very elegant corner. Would be interesting to see if we could make this kind of corners, beautiful corners, simple with a proper thermal performance today. And this is endless. I put a lot of Witscan because he was one guy who really spent his life thinking the window as not only as a construction problem, but you see the details are very sophisticated, but as a concept in itself, right? And this is only two examples, the Philips extra library, which windows are both window, you have the clerestory, you have the more kind of room, the window becomes a room itself, or the Fisher House corner, in which it is difficult to know where is the window ending and where the room starts, right? It's kind of window, room, furniture all together. That means that windows are much more than just this 1.5 by 1.5 opening with two-sided windows, right? So that makes a lot of the architecture. And then that finishes lecture 10. We were on time in spite of the technology. I hope I can just remake the videos in one clip. By the way, if you didn't notice, last week the video was cut. I did the last 15 minutes as part 2, so you can find in YouTube. I will not repeat it because I think you can find there the John Lim's secret detail and other questions. So please look at it because we can ask about that in the exam. This is also matter. And well, curiously, those 15 minutes took almost 40 minutes. Doing them slowly, right? So this is like a 2 hours worth of this lecture in just 1 hour. That said, this is where I took most of the details and the references, right? This is interesting. This is a set of books which you can find in the library here, in the science library, which has a lot of great buildings. And then that's all for today. If you have any comment or question or request, please write it. Tomorrow we have a very busy day. And this afternoon I have to go outside to one critic, so we have no time to prepare many things for tomorrow. But we will announce the next assignment and we will speak about a midterm, which is getting closer, okay? Thank you so much and see you tomorrow.